This video is about capacitors and capacitance. Here a few capacitors, different types by the way. Here ceramic, perhaps also here ceramic. Here there is a kind of plastic layer inside that capacitor that forms the di-electricum. Here high quality plastics, etc., etc., that form the di-electricum, etc. So it's about capacitors and capacitance. It differs. They differ. Of course, capacitors realize a certain capacitance, but the whole idea of capacitance is much more broad. When you look at old books, say even from a few centuries ago, the whole idea of capacitance was already discovered in a scientific way. And it was all about, say, these things. Two plates here, two plates on a certain distance of each other, and the idea was, not only the idea, but in practice it also worked, that you could store charge in between these two plates. Say when they were connected to a voltage source of whatever kind, say via an electrifying machine. You can surely find more information about that on the World Wide Web. It's the kind of classical way during the 1800s, 1700s, when these capacitors were tested and discovered at its first days. And that means that, say, a kind of charge can be heaped up between the positive and the negative plate, and say when that charge is heaped up afterwards, and you connect, say, the plates with a switch or so, the DC current, say, the charge that is heaped up inside that capacitor is, say, short-cutted, and it means that an electron current starts to flow. This is the switch, by the way. So when you do this, say when you have a capacitor of whatever kind, could be in a microfarad range, say 100 microfarad, 220 microfarad, 1000 or even 10,000 microfarad, and when you, say, charge that up via a voltage source and then shortcut the plates, you will surely see an effect, say a spark here. And when, of course, when you have connected here a voltmeter and here a current meter, an ammeter, when you do that experiment, you will surely see that the ammeter pointer moves very fierce, and the voltage drop will also be, say, visible. Say at first 100 volts or so, or 20 volts, and then when that capacitor is discharged via this switch, the voltage drop is visible and goes to 0. So, well, it's perhaps a sloppy video, but anyway, I want to say tell something about capacitors, etc., because they are always used, everywhere used in electronics, etc. About the, say, the value of the capacitor is related to the surface of the plates and the distance between the two plates and the material in between. Say, with when we use air as the dielectric surface, material, I say surface but I mean material, we can use this formula. It's a formula of an old book that I've more or less always used in the past, and here we see the formula, and it's very important to see and to tell that the material in between the two plates, and I've thought here it was air, but there are many other materials that can be used as, say, a di-electricum, say a material between the two plates, have different properties. That also means that the capacitance of such a between these two plates changes regarding the material that is in between the two plates. And here there is more or less a standard idea of the di-electrica. Perhaps, I don't know whether it's visible from this distance, but anyway, let me talk a little bit about it. Bakelite, the dielectric constant is 4.5. Glass, it has a dielectric constant of 5 up to 16. Paper, 3.5 up to 5. Quartz, 3.7 up to 4.6. Petroleum, 2.0 up to 2.3. Porcelain, 4.5 up to 6.5. Rubber, 2.7 up to 3.3, etc. Distilled water can also be used as a di-electricum for between two capacitor plates, and its dielectric constant is 76 up to 82. Anyway, well, that tells a lot, say, about the properties of a capacitor. I wipe it out again. It's a little bit sloppy and I don't like it. I've talked about the formula of the di-electricum. I've talked about the distance between the plates, etc. Well, say again the whole idea. Two plates here. Two plates, between there is a certain distance, there is a dielectric material between the plates. Could be, like I told, everything, air, ceramic materials, etc. And perhaps it's interesting to show that we have here, for instance, such a ceramic material in between two plates. This capacitor is 100 nanofarad. Well, why does it have such a high value when it is so tiny? That has everything to do with the properties of the ceramic material. in the 1950s, 1960s, many very specific ceramic materials were invented and tested. And when you look at the scientific literature about all these ceramic materials, it is a sea to drink, really. Very specific materials were in the past used. Ceramic materials were used to make this di-electricum in between in that capacitor. These are normally used for, normally, I say normally, but often used for, say, low voltage circuits, etc. And when we talk about the di-electricum, there's always, say, an idea when the voltage between the two plates get too high, there's a breakthrough. And of course, say, when you use this tiny capacitor and mount it in a circuit where the voltage for what it was made is too high, it will break through and perhaps can be damaged. Sometimes it can be damaged. Anyway, there are also, say, self-healing capacitors. Could be that this is a self-healing capacitor. It means that, say, when there is a too high voltage on certain parts inside the di-electricum, and in that case it could be plastic or so, or other, say, high quality plastics. We have here a layer and another layer in that capacitor, and when there is a voltage drop here, say a spark, one plate, the other plate, the capacitor heals itself by, say, repairing here these two places over which there was sparking. Well, that's a completely new idea, sorry, not a new idea, but another issue. And I wanted to, say, keep this all more or less basic. Well, there are different materials as di-electricum, plastics, ceramic materials, air, oil, all kinds of oils, of course. In the past, the very past, that's what I mean, oil was used for, say, high power not electrolytic, but high power non-polar capacitors. Anyway, I've talked about the plastics. Here you see, for instance, a high quality modern capacitor, and here again, say, a capacitor with modern plastics inside, modern plastic materials. Hope it's visible. It rolls away. Here again, very high quality capacitors, and all these capacitors, their di-electricums have different properties, though the value, say the capacitance value, is more or less always the same. So you have a ceramic capacitor of 100 nanofarad, but also, say, a kind of this plastic capacitor of 100 nanofarad, etc., etc. Here again a small ceramic capacitor. Ceramic capacitors are always used in high frequency circuits, and important to tell, sometimes a radio oscillator does not want to work with a plastic di-electricum capacitor, but only with a ceramic di-electricum capacitor. Anyway, thanks for watching. My camera runs out, and thanks for watching again. It's only say kind of first idea about capacitors and capacitance. Thanks for watching again.